I think we spent the first part of the resonance unit on the most common form of resonance, by far the least powerful one, the idea of an additive resonance versus multiplicative. That's the important thing here. The case of the mechanical resonator as a model of a cyclotron, this would be the usual situation where two pole halves, plus and minus, be oscillating and make the orbit bigger and bigger. Just like our other more mundane examples of a spring and a mass and a force, cause the phasor amplitude to grow with an Archimedean spiral. That is, each revolution gave you the same increase in amplitude. When you do multiplicative, and that would what you get if you had a cyclotron that could oscillate the magnetic field, then the spring constant is the thing that you're wiggling. And when you wiggle the spring constants, that's multiplicative, as opposed to being an inhomogeneous term. This thing is actually inside the equation. And except for the fact that this is the time variable, the independent time variable, to make that a space variable, this is Schrodinger's equation. So this is a really very, I would say, unusual analog of the mechanical systems that we'll talk about here, and quantum mechanics, that is the wave mechanics, that you learn first in most quantum mechanics courses. So I want to do that and show you that, and we have quite a number of spectacular simulations that go with this. This is also bringing us back to the trebuchet, which is a combination of translation and rotation. We'll see some of that appearing in a simpler form. Now, most of mechanics books that mention parametric amplification use a really complicated example, and that's a child on a swing working the rope as they're swinging and making the amplitude go up. And if you've been such a child, and I think everybody has, you know that it takes a little bit of work, and it's not spectacular. You don't fly off into the distance by doing it. This causes exponential growth and a logarithmic spiral. It's powerful, and so that's what we want to see here when we look at the simulations and the analysis as well. But the other thing I want to talk about is higher symmetry oscillations. This is the beginning of using group theory to solve mechanical, but also quantum mechanical problems. These all have analogs. And we were just talking about an analog that involves spin coupling. And that's a big deal in this building right now. And if you went to Friday's seminar, you saw this a talk on that. And we'll see if we get it far enough down here to look again at the fractional revivals. We've seen that already, so if we don't make it today, that's fine. It's going to be in the lectures that are posted, so you can play with it. Okay, let me point out that there are a number of links that go with the animations that we have today, and I have them posted on some slides that come later. So anyway, this is the additive resonance and the multiplicative one. This form, as opposed to this form, has the exponential growth. And just to make the story short, the thing that I am proposing here is that to understand parametric amplification and Schrodinger's dynamics, really, is to, instead of moving the fulcrum of a pendulum back and forth, that would give you basically the linear resonance. Moving it up and down and doing it just right is explosive. That is nonlinear. So that's what we're going to talk about. So I'm going to just jump ahead to the beginning of that on these three screens here. And this is that picture here and here. So this is what we're going to be dealing with. We're going to be in comparison to what we've already done. And of course this is forced harmonic oscillation with no damping. And we're not going to be putting any damping directly into this one, but in an actual real-world situation, of course, it would be there, but it's even less significant to what happens for this than it was for this. We studied the damping pretty carefully there. Now I have something called the nasty equation, which is a combination of these two, and that's something that could be moving in any direction. And the basic idea of that nasty equation is that maybe we should be thinking about building a device that would let me put this at any angle. So I could be cranking it back and forth like this to show linear resonance. Then I could turn it up like this to show the explosive resonance of a trebuchet. Or how many of you have ever seen the Arkansas whirler? Have you seen that that's available in places like Eureka Springs or Dinosaur Park or something like that? It's a neat trick, but basically what's happening here is you're wiggling a little thing here that is doing a circular resonance, and this propeller literally explodes if you do it right. You have to hold the thing just the right way and pinch it and then stroke it back and forth to get it resonating. It's a neat toy. Nice piece of mechanics. But what we're going to do today is go ahead and make the connection between these two algebraically, so that we really get to study the mechanics, the derivation of Schrodinger's equation in a very strange way involving this system, and then showing it's the same as this one. So I call it the jerk pendulum, and the applications that simulate this all have the name jerk it. I mean, everything has it because of the face-it interface that has been with this thing until we went onto the browser and HTML systems. Anyway, good old Schrodinger's equation, energy minus the potential, is a function of x, and a second order differential equation in x, and setting all constants m and h bar equal to 1, so it has that simple form as opposed to a more complicated form with 2m over h bar squared located right there. So you've all seen enough of this in your quantum mechanics classes. Now let's marry it to this pendulum that's being forced to live in an accelerated frame. That is, we're going to put artificial gravity onto this pendulum in addition to the constants that's already there. So this would include that, the actual gravity. But we'll consider a case where that's really quite small compared to this. So that's what's going to happen. And then the acceleration, well, for most of the things that we'll do today, we'll just take one Fourier component. That is, we'll have one frequency. The periodic acceleration that we're going to be applying to this thing will have the frequency squared of the oscillation that we're applying. Okay? So, that just then lets us, we've got to marry this dynamic constant here to the potential amplitude. And we're thinking here of a crystalline potential. Actually, this is called Matthews equation if you just have a cosine for a potential, and that's the very first representation of a one-dimensional crystal or solid, just a cosine potential. Okay, so we haven't paid maybe that much attention to that, but the thing that we're solving is in time as the independent variable. Some people call, I think that we just had a Physics Today come out with a cover story, and it was called Time Crystals. The idea of crystal in time dimension. Okay, that's what this is. Very simple example of it. Okay? So, let's get these things synced up here. And go ahead and to try to make the Matthew equation work for us in time as an independent variable, as well as it works in the space a variable, independent variable. Okay, so that's our first connection formula right there between these two very different physical systems and phenomena. Okay, that's the first connection relationship, basically between the omega y t and then this nx right here. So our cosine will have an adjustable parameter that makes you have more wrinkles in x. Well, we're going to be able to adjust our periodic acceleration as well. Those will be very critical parameters, and they require extreme precision in order to get various effects that we're looking for. So the next thing is if you just go ahead and say, okay, I would like nx here, that's n dx, the differential of that, to be omega y dt, and then go ahead and get the omega y over on this side. So that's my differential of time that I'm going to be playing with here, and I need it squared. So that's what's going to be in the denominator of the differential operator right there. And that will put the omega y squared, since it's in the denominator here, I'll put a numerator right next to that. So that will make the equation a little simpler, and we'll get a connection between this coefficient and the acceleration factor for the driver of the parametric amplification. So the parameter here that's being amplified is basically this is the thing that's driving it, but it's this artificial gravity. As you jerk this thing up and down considerably more than 1g, this thing will be having an effect that's very much like the potential here. Now, one of the things we're going to be getting here by solving this equation of Matthew, or this one, and it's Matthew's equation in time, one of the things that we're going to get are energy bands and energy gaps, which you see in solid-state physics at any number of dimensions. We just have one dimension to play with in the independent variable. So if you do that, then letting this be 2, that is, letting the symmetry index, which is really what it would be if I let x be on a circle to make a closed ring crystal, 2 is enough to get you what are the edges of the band. So we're going to use n equal 2 for everything we do today, but it obviously could be some other integer just as easily. So that is the key pretty much right there to the connection formulas that we're deriving here, and let's go ahead and put them up here. The first one is that the coefficient that's called the energy eigenvalue for Schrodinger is going to have this form here. So it would be a product of n squared, well, n equal 2 makes that a 4, and then the omega y squared, this frequency, will determine what's happening, but it's in the denominator. The square is in the denominator, multiplying what would have just been the constant term for this Schrodinger equation that makes plane waves. If you don't have that cosine in there making it up, that's what we're going to start with as we work with this. and it will be, only it cancels there actually, the VO, the coefficient of the crystal potential, the amplitude of the crystal potential will be this value right there. And if we go ahead and take the value that we're going to use, that's VO is 4 times A. So the VO and the acceleration are proportional to each other. And it's very simple, where we take L equal to 1 also in this connection formula. Okay, so with the L equal to 1, that makes it a little bit simpler, the algebra a little bit simpler, but that's okay. We use that as our length scale for the pendulum. Okay, so that's all the algebra that we really have here, and we just have to solve it. And solving it is not as hard as you might think, given that we've got computers that can do matrix diagonalization. Otherwise you get in a horrendous mess, and that's why this isn't talked about very much. Continued fraction solutions, which are really terrible. They're very imprecise, and they're a lot of work to get. So this is very, this Matthew equation is not popular for that reason. Okay, but for the way we do it here, it's quite popular, because all we have to do is make solutions for the case where there isn't any potential there. This is just plane waves in space on the left, and plane waves in time on the right. Okay, so that's what we're working with. Those are the base functions, and then we'll just build up the solutions to the differential equation by Fourier analysis. That is, we'll use Fourier components. These will be our Fourier components that come here. This right here is just in terms of the length, and we'll suppose that there's periodic boundary conditions between 0 and L, that the potential, whatever it is, that is matching the oscillation over here, is going to have a definite K value, that's waves per meter, and this one's going to have a definite frequency, waves per second, that is radians per second. So, excuse me, this weather is getting my voice. The matching of this to that and our frequency for this pendulum, and we'll be simply solving this thing with the coefficients that we just matched for the two cases. So the idea is that this periodic boundary condition here means that this, whatever this potential is going to be, it's going to repeat after L perfectly each time. And this one is the pendulum, and we're asking it repeat perfectly after a time, whatever capital T is. So those two are analogous. Let's see if there's anything else I can say here. I think that that's the basic idea. So the Schrodinger equation with those bases, within this basis right here, this is just writing it out in terms of K bases labeled by integers. Very simple way of doing it. And we're going to do the same thing with the time equation that goes with that. So it's just a matter of matching those up to get a matrix. We're looking for this matrix right here, the matrix of the entire Schrodinger equation as its cosine in it. So that's a pretty elementary thing to do. This is the kind of thing that you see in any solid state book that begins in an elementary fashion like this. And basically we're asking for the integral here of that potential between a particular value J and particular value K of the spatial variable, if you were solving the Matthews equation in space, the way that's normally done. So that's a fairly easy thing to do, and the answers are pretty simple, and they come out in a very nice fashion. I'm going to move all of this stuff to the top of the screen here. That's what I'll do right here. Get this thing to the point where I have the matrix elements that I need for the Schrodinger operator. That includes the term that's multiplying the wave function and the one that's differentiating it twice. So that is what we're after right there. And it's pretty simple. This is the matrix. Now, it goes in positive and negative directions forever, so you might say, I can't possibly do a matrix, it's infinite. But what you can do is just start and look at the diagonal elements, and I see two here that are equal, so I'm going to probably have to solve that one just to get started, and then maybe I'll add that as a perturbation. But what you do is you set your computer up with a matrix that's only that big, and simply ask it to diagonalize it. And you get really close to the answers that you need in that neighborhood if this is small. As this gets bigger, well, you might have to go a little further. As this gets still bigger, you might have to go further still. But that's a very convergent process that you ought to know about, because it's something you do on a hand calculator or a Mac or whatever. Okay, so that's what's going on right here. We're working with matrices for J and K even and J and K odd. That's because this thing has symmetry. We work with the ones that are going to be antisymmetric and symmetric. So here you just start with 0. That's the starting point for the thing, and then you get a 2x2 matrix involving those guys, and then you get a 4x4 and so on, 6x6 matrix to solve. And then the connection relations that we stated are at the bottom here. So that is the trick, and here are some solutions that we're going to look at. And we're going to compare what we already know about those solutions. They're pretty simple up to a point where you don't have very much of this parameter at all. That parameter nu is the V0 amplitude, potential amplitude, half of it, and then that's for the acceleration problem of the pendulum. That's the amplitude of your acceleration that's going up and down with holding on to the pendulum. So we use just 2 times that divided by 1. We're going to keep L equal 1 in all of the stuff we do here. Okay, is that making a little bit of sense? The basic idea of this is pretty much shown there. Okay, and this is some results that I'll talk about in just a minute here. Okay, does this make some sense? It's kind of strange to be doing mechanics with quantum mechanics. Okay, that's weird. All right. Okay. Well, here's some examples. These are things that we're going to simulate here. But here's just a case to get an idea what kind of eigenvalues we get for vehicle 0.2. That's pretty weak potential. I start to see my Bohr orbitals. That's what we start with. Bohr orbitals whose energies are 1 squared. That's 1. Well, it starts with 0 really, but then 1 squared. These two are close to 1, but they've been split apart by the potential that's very effective when it's small. And then the next stop after that are 2 squared, which is 4. So here's 3,999. It's almost 4. But a very tiny splitting for the second pair of levels. And I'm using standard spectroscopic. I apologize for that, but it makes sense. You see that it does. And then the next stop after that is 3 squared. Well, you can see that only to the 4th figure here do we have to worry. This thing is hardly splitting at all due to this perturbation. And that's what makes this thing work. It's very convergent. Okay? Now as you go up in the amplitude, that's this crystal field is being perturbed, you start seeing quite a deviation, and they start to go negative. And when it goes negative, it really means something. It's different for the mechanics, classical mechanics, than it does for the quantum mechanics. Nevertheless, the numbers are valid in either case to a high degree of accuracy. You can see already the 3 splitting is in the second decimal point there, and the 2 squared, that's 4 splitting, is quite significant. Well, it helps to plot these things up as we're going to do next, just to get a feeling for it, and then actually look at the results. Now, see if there's something here that I need to say. Wiggle frequencies for the pendulum. And in order to get that, I have to take the eigenvalues I get from this and take the square root of them. So these are all square roots of that number. If it's an inverted thing, I change the sign before I take the square root, so I get a real number, and we'll see what that involves. And the same one here. And these will involve a pendulum that is stable upside down. That's what's so peculiar about this, the classical mechanical analog of this thing. That's what I want you to see very quickly here. Okay, well let's just go for it here. This is what we're going to be dealing with. This is a plot of the eigenvalues just for this n equal to 2. If I make it there, then all I'm interested in are the lines that are boundaries between regions where the wave function is unstable and cannot exist, the so-called gap of a band theory. And then the bands themselves, where it's colored green to indicate that's where the wave functions can go. And you start off here talking about 0 squared, well 0. There's just one level right there that takes off for the basement very quickly as we make the potential deeper and deeper and deeper. Remember, the potential is a cosine that depends on what frequency or k vector we assign to it. But in any case, that potential is fixed for each vertical section here. We see immediately a linear splitting of the 1 and plus 1 and minus 1 right there. So that's the first gap, and it happens linearly. All the rest of them happen non-linearly. In fact, this one just stays closed until within a pixel, until you're way out here with a potential of 3 or 4 units. But a potential of just 1 unit like that, that's what you get right there. These 2 band edges, and then a continuum of possibilities in between there, and then craziness, chaos here, and then a pendulum that sits up the way pendulums normally sit, but does it stably from here to here. And then right in this little region right here, if you try that energy out, the pendulum would start out like that, but then go crazy, go become a trebuchet throwing things violently. So that's what we're going to see. So all of these green regions here, if we're talking about this particular vehicle 2.0 bands, the stable hanging modes lie in this region. So there's lots of them. Then there are quite a lot of these right here. They're very stable and hanging. And then right here, this one is interesting because every one of these in here, and particularly the ones that will be right there, are stable upside down. Okay, well, seeing is believing for this. So let's go ahead and look at some of the, this is just the functions. I'll go ahead and put that up on the lower, this one down here. And then that's some of the waves that we're going to be looking at right there. So I'll leave this one with a parameter, and then I'll go with this one. I'm sorry. I'll go with this one back. I'm sorry, forward. And we'll try this very first. This is the 1 plus case. It might be worthwhile to do 0 plus first. Let's go and look at what happens right in there, right about there. Okay. So I will start the 0 plus simulations. Hopefully that will give us something. Let's see. Oh dear. So
Let's try your other Mac real quick.
Pardon?
Try your other Mac real quick. Well, looks like it's live.
No, we're live. That's UARC Wi-Fi.
Back out and go back in.
Let's see what.
Start new session.
Well, it's going. There
Right.
it is. That's it. It's working. That's the correct link right there. Okay. Now, it's already gone off screen, so let's just go ahead and restart it. But you can see one of the things that happens with this is that it doesn't take account of the pendulum's shift in this direction. It's mostly interested in its shift up and down. So this goes crazy. This starts being a trebuchet fairly quickly. I can start it, right about there, and it goes very quickly. I was off center when I started it, but if I start the thing right on the thing, it stays stable for quite a long time. Now, I should mention the classical mechanics that circus performers and people that can ride on a unicycle use. And they probably wouldn't use this mode until they got really good at it, but this is a mode where just by pumping your body up and down, you can maintain yourself in an upright position on a single wheel, a unicycle. So we're going to be looking at all of the various modes that a unicyclist has to get into his brain so he can remain stable upside down. And it's really hard to do the upside down ones when you're way out on high amplitude. They learn to do that pretty well too. But mainly it's in this region right here that they live in fashion. Now let's go back here. I'm going to pause and go back to this. And let's take a look at this one right here, the B1 mode that this has. Arg. Why is it doing that? Try again. There we go. Oh, that's just the one we just looked at. Now, I think, I'm not sure. Let me just start it again on this side and see. Now, you see, over here, that's the actual acceleration curve, but it's the potential with the right scale factor. And so this is a typical wave function for that thing that has, it dies off on this side and then has a peak in this region right here, and that's because the plus and minus signs have shifted. But obviously this one has done its trebuchet motion. I can go ahead and just start it again here, and you can see if I make a big amplitude like that, it's out of here very quickly. Okay, that's not a good solution to Schrodinger's equation, but we're doing the Schrodinger equation just for small angles, either close to pi or close to 0. And for those, we're getting wave functions that match what Schrodinger would have in space. And of course, we're working in time, which is much harder to get stability anyway. Okay, so let me pause this so I don't eat CPU, go back, and hope I can pick up on the next one right here. And for some reason, I can't.
Try it on the other Mac. Sometimes our internet works on one, but not the other.
I don't think the Wi-Fi's on, so do we need the Wi-Fi?
We have been having issues with Wi-Fi, but obviously we're getting something that works. Let me go ahead on this one right here and see if I get it to it, and we'll bring that one back to show the pictures of what it is we're dealing with. Let's see, this one, as I recall, is very stable. Yeah. So this is the other side of the band. Okay, this is a wave. It's kind of a neat wave function. There it is, making a node, then an antinode, and a node, and an antinode. Within this potential, this cosine potential, and it is very stable. This is the one that a beginning unicyclist can work with. You can go up and up and up like that. You gotta go anti-symmetric. That's the trick to making yourself stable on a unicycle. It's kind of cool. Okay, so you don't get parametric amplification, because parametric amplification is going to put you in the hospital. They will not sell a unicycle, at least an honest cyclist store will not sell a unicycle to somebody like me. And probably not you. You really ought to be about 7 years old when you start this. So when you fall, you don't get hurt, right? If you're a big guy or girl and you fall off a unicycle, well, if you know how to fall, it's okay, but when you don't, break things, right? So this is the way you don't break it. And this thing is really amazingly stable, even with high amplitudes. It's just that it's not obeying Schrodinger's equation very well now, okay? And it's also making explorations off into the hospital region here, or what's going to be the hospital region for unicycles. So this is the part of the spectrum. We've got the top and before the bottom of the band, and let's get that picture. Well, we have it on the screen down there, but let's get it on this one, since this computer seems only good at doing that sort of thing. There's the picture of the whole band structure. And we're looking at this band right here, which is the band which has the inverted values. And you can see it's sort of working its way out to fall apart, but it quickly recovers. Oh, there it went a little bit further, you see, and so it will eventually destruct. But it stays there for a long time. I can take it out there and show you that it is really quite stable. Okay. It takes a long time to get outside of what it reaches in the first few throws there. Went a little further that time. But still, this sort of shows you why it's possible to learn to ride a unicycle. Okay. Now the rest of it I'm going to show you isn't spectacular, because we start with the unicycle down and just be thankful that it doesn't turn over. That it doesn't go into it. And let's go ahead and I will bring this thing back after stopping it, pausing it anyway. Oh, it's getting there. It's got about ready to go off there. Now, I'll go back here. And we'll pick, this was a very nice one, because this one pretty well gives you a Schrodinger wave. And you see it's matching the potential. There's where the curvature is very close to zero. That's where V minus E is pretty close to zero. So it makes kind of a square wave. That's a Matthews solution that's kind of well known. Okay? And you can see what the pendulum's doing. And it's very periodic. It takes a very long time before the fact that it has a Y motion that the Schrodinger equation is not supposed to have starts to broaden the curves there and take it out. And this one, I don't know, I haven't waited long enough on this one to see it go crazy, but it's headed that way for the, what I call the nasty equation. That nasty equation is actually having both y and x included in the pendulum's behavior. Okay, so that's this guy. This one's not bad either. This one has a minus sign on it, so it's anti-symmetric with respect to the center of the potential well that it represents. I pause this, go back, and start this one right here. This is the 2 minus, so-called A2. If you take my group theory class, you know what all of that means. And I can start off with a much higher amplitude than that. And I can do it on the other side too. And it makes the same wave, except for a factor. That's what the linear differential equation behaving well in its linear region, okay? But it is growing, you see, and that's something that wouldn't happen for a pure Matthews solution, okay? So that's this particular wave function, the red thing there being the dot that you see in here, what just went off screen, okay? So you can see it here growing. And these are all kind of neat. I'll show you one more here. That's very, very stable. And remember, the setting of the amplitude for this nonlinear differential equation is very important. The tables that this thing makes, let's go back and remind ourselves that you have to know exactly what value of E to put in there. You have to put the eigenvalue that you would get for the Schrodinger equation, the energy of the Schrodinger equation, the E that goes into E minus V. And you have to set the potential to just, the potential and the energies have to match. This is an eigenvalue problem here. And so we're getting, anyway, we've run this one long enough to see what's going to happen. Started off going this way. It's going to end up going this way. So it actually switches, tries to switch its symmetry site, its starting symmetry site itself. So incredible solution, all sorts of weird things that are beyond what we're going to be talking about, but just the main idea of being able to operate on a inverted or ordinary pendulum while it's going up and down, being accelerated. This one is the last one here for this particular setting of the potential. But this is something I recommend you to play with. This one makes the wave function's maximum come out right where the potential minimum or maximum is. Okay, this one matches that. Okay, so and again, this is one that I can, I can be pretty squirrely with it. I can bring it out quite a distance there and have it make a pretty nice wave function. If I take it too far, well, you start to see it degenerate, but still very well behaved. But of course, we're up in the regions where the splitting, the band gap is, pretty small. So the wave functions that we make this are very stable and matching the potential nicely. Now you can see it sort of bends the other way. If I take it over the other side, it's the same thing by symmetry. Same wave, just with a phase minus now. Now in quantum mechanics, you'd have to pick a wave function that was normalized, right, in order to make use of it for various calculations. And you could pick a plus or a minus, it wouldn't make any difference as far as calculation goes, because you have two of them in there and the phase would not change. But anyway, this is, I hold this up as the most bizarre connection between a purely quantum mechanical, and I mean elementary quantum mechanical thing, and a bizarre piece of mechanics, basically the mechanics of the trebuchet. Now anytime I take this thing and try to do an inverted guy, wait a minute, let me see if I can grab him, get him, take this guy up to here, throw him a little bit, okay. Yeah, I'm going to go unstable, okay. We wait long enough and this thing will die down briefly, but it's basically chaotic motion. Okay, now we're going to give it some energy, right? And that isn't quite enough to get over, but so this is exact description of the oscillating pendulum, oscillating supported pendulum, but there's no quantum mechanics. This is the nasty equation right here, where we are looking at both terms in the nasty equation, both the sine and the cosine, both the x and the y. It's the behavior near 0 or pi for the pendulum that is matching the quantum mechanical things. All the rest is chaotic motion. And if you were trying to run a unicycle at this frequency, you'd be on the floor pretty quickly. Okay, so let's. This is just something. If you love mathematical physics, this is just full of effects. It's just something everyone should have to play with, but you're lucky. You have a very small crowd of people that have this at your disposal, and maybe it becomes useful for something later on. So let me pause and get us back to the rest of what we need to talk about today. So I will bring this one home as well. Let me, for some reason it is not responding, so I'll bring it back by force. Okay, there we are, and then I'll play it. Okay, and I gotta do it with this one too. All right. Now, as I said, if you just take a random settings for any of the possible settings, and there are here cases. We were just doing a very small potential. It really gets wild as you go to bigger potentials, and you ought to try these. They're really quite remarkable. So worth doing. Okay. Oh, and it's also workable if you put more Fourier components in. If you make something that's close to a square well, in other words, if you were to be a unicyclist, that would remain one thing, and then drop to another position and hold it, and then come back like that, you still could be stable. There are stability regions for this one. And particularly up in here, it's really weird because you have a gap within a band. So that's interesting quantum mechanics right there. This comes out of the quantum theory for computer age textbook. It's bizarre. And then here's some more of these. These are actual bands with the levels that lie inside of each band for a closed set of potentials. That is, if you require this thing to repeat after 6 peaks, this is the kind of behavior that you would get for the actual eigenvalues, and approximately for the inverted pendulum or the hanging potential. Most of it's hanging pendulum. Okay. Now, what about symmetry? All this plus and minus stuff that you see on these designations. That's standard spectroscopic notation for wave functions, symmetry of wave functions. Let's go back to the thing that we've already talked about, bilateral symmetry, okay, the balanced case, where our Hamiltonian, now we're thinking in terms of spinors, little 2x2 matrices, or square that thing, you get this, right? That's the K matrix for a classical problem. This is the Hamiltonian, really Schrodinger matrix for a quantum problem. So we have the simplest symmetric case, the one, the B case that we talked about before. That's two equal masses with equal springs constants, and then whatever in between there. The off-diagonal term B indicating how strong or weak is the coupling spring for two oscillators. They're frictionless and all that kind of perfect stuff. So that's what I want to carry on a discussion of here. Now what I wanted to show you, and this is, I think is an important piece of mechanics, but really important piece of quantum mechanics, and that is that the really complicated objects as far as spectroscopic properties and resonance go, they're usually symmetric objects, so they have symmetry. They have, let's say it in a crude way, they have symmetry, as S-A-M-E. A lot of things that are really the same, if you're talking about a couple of electrons, they're really the same. There's not any mark on either one of them that would distinguish them. And that is, in itself, magical. But then if you realize that they're waves, here's a wave, there's a wave, and a given amplitude that you have from normalization or whatever, they've got to be the same. See, so it isn't so amazing when you think of it, but then you realize it's an incredibly complicated wave. An electron is an incredibly complicated wave. Then a nucleon is even more so. We don't really have the answers to all of that. And then any molecule that's made out of these things, also, barring some mislabeling of it or whatever, some impurity, absolutely the same. As every methane molecule looks the same if you have the same isotopes. Okay? So when we talk about something having symmetry, we really mean it in quantum mechanics. Whereas in classical mechanics, it would just amount to, I have a good machinist here, and he machines this thing out, so it's good to 10,000ths of an inch, right? But then all of the molecules and atoms and things that make up that piece of bronze, right, they're completely different from this one to this one, right? It's a mess. Classical things are a mess when you get to looking at them as finely as you do when we're doing our nano work around here. So, with that said, it makes it important to find a way to find solutions for things that have a lot of sameness, which means they're things that have a lot of resonance. And the resonance is what really makes the thing hard to solve. That's really what it boils down to, is that having a thing behaving according to resonant effects complicated. So the most difficult problems to solve are often the ones with the highest symmetry. But if it has a high symmetry, there's a cure for it. The cure is the algebra of group theory, the algebra of symmetry analysis. Now I'm being a salesman. I'm trying to sell you on symmetry analysis. I've been doing that all my life. Ever since I discovered that I could solve something that Feynman couldn't solve by using group theory. That was what really let me become crazy with this stuff. Okay. And then it just kept growing. I kept being able to do things. I'd see something at a conference. I'd say, hey, you know, if you did this and this and this, you could figure that out. And that thing that we did was a symmetry analysis. So I'm also advertising this point, the course that we'll be doing in the spring, which is a repeat of the group theory. 5093, I think, is the number, whatever. Anyway, think about signing up. Anyway, here's just showing you with the simplest symmetry, that the solutions are just sitting there. The group theory, if you ask it nicely, will tell you the answers to your eigenvalues, and most importantly, where most of the information is stored, the eigenvectors. Now there's only two of those things for this, as you know, and you already know what they are. But let's just go through the machinations that occur. Basically what you do is you have an operator that belongs in a symmetry group, an operator whose square, that is sigma b times sigma b, is 1. And that's its minimal equation. So if it's got a minimal equation, an algebraic equation, I can factor that into projectors. And those projectors will project the eigenvectors. That's all there is to group theory in quantum mechanics. Well, there's a lot to that, but that's a basic idea. Okay, so we get two projectors here, and the normalization, you use the same procedures that we talked about before. For getting that, there's one factor, there's the other, but they both need a 1/2 in order to make a projector that's idempotent. That adds up to 1. The projector has to be complete, as well as orthonormal. Okay? So the product of these two with each other, 0. The product of this with itself is itself. And the sum of the two is 1. And that's the sort of thing that all of the symmetry groups that we'll look at today have that, obviously, more or less obviously. So I take this initial state right here where only one of the objects is off position, the other one's still at home, which is its 0 equilibrium position. And I apply the projector to that, and I get one of the modes. And then I apply the other projector, the P minus, to the same state, and I get the other mode. So that's basically it in a nutshell. And here it looks very trivial, but you can imagine if it's something like buckyball or SF6 or methane or some other molecule that has a lot of symmetry, there's a heck of a lot more to it than just this 2x2 transformation matrix and I'm making it a phasor matrix. There's a symmetric state, there's the anti-symmetric state. That's what we dealt with when we did the 2 oscillator example. And this is what you'll do on the homework, right? There's a B problem at the very end of the homework that you should be able to zip through and then name properly. Okay, so let's bring all this stuff up to the same level, because I want to show it for 3. What happens with 3? Okay, if you have 3 masses that are on sliders and there's no friction, what would be the modes for this? So right away you need the multiplication product table for this particular symmetry. The symmetry that consists of 120 degree rotations. The one before has 180 degree rotations for the symmetry operator, and there's only one of them, so that's pretty easy. But here there's a couple of operators that have the rotational symmetry that is needed for something that has 3, that is, or a third of a rotation instead of half of a rotation, like we're seeing on the stuff down there. Okay, so this one I'm taking off and starting with this one, and then there are the coordinates that go with these 3 rotations. That is, I start with something, I call this the my number 1 mass, or my number 0 mass, and I pull it out to any position. That's a distorted object that has a state indicated by a ket with, that's the origin. That's the origin of the symmetry possibilities. Then the next one, which is a 120 degree counterclockwise rotation of this one, is this one, and that's one that has a unit displacement in the second position of the state vector. This one had it in the first. And so forth. The next rotation by 120 of this would take it to here, and that would be the unit vector number 3. And you would get that unit vector if you did the other rotation that's 120 degrees the other way, that is left-handed. If I take this thing up to here, I get this directly. Okay, so that's just to get familiar with what these little r to the first power and r to the second power, which happens to be equal to r to the minus 1 power, that is what you see for this coordinate system. That's really what that is. Now, this is just a picture of where the various operators take you. R1 goes this way, then this way, then this way. The other one goes around the other way. So it's just a direction of rotation map for this particular object. Okay, so what you realize right away is the minimal equation for all of these rotation operators, not for the unit operator, but for r to the first power or r to the second or inverse 1 power, the minimal equation is the cube has got to be 1. So in that group table, the cube of the r will take us back home again. I go around and around and then back home again. So that has some eigenvalues, the eigenvalues of that group operator, that is the third root of unity. That's e to the m times 2 pi over 3. Raise that to any power, and that will give you all three roots of this particular operator. So that's this eigenvalue space that you work with. That is, the minimal equation of this operator is written out right here in terms of e to the some integer times 2 pi over 3, and the only integers that work are 0, 1, and minus 1, and we're done. We don't need any more. So what we have here is the time to make an operator out of this thing by dropping a factor, then dropping another factor, and then dropping. That's the way we made the 1, 2, 3, 4 matrix give projectors. But this one turns out to be a lot easier. What we do is we say, I know that when I get these projectors, they're going to be complete. That is, they're going to sum up to 1. That was sort of a magical thing that occurred for the 1, 2, 3, 4 matrix after we got all done doing things, but now we're going to make use of that. And then once that's true, I apply r to this equation, and I get the eigenvalue that goes with 0, 1, and 2, namely e to the 2 pi I m equal 0, 1, and minus 1 or 2. Okay? And then if you square it, it'll just be that squared, which is just those numbers again, but now rearranged. So what you see then is that it's really quite easy to write an equation for the group operators in terms of the projectors, and that thing is unitary. So all I have to do is take the complex conjugate and transpose each one of the numbers that occur there, and I produce the actual projection operators in terms of the group operators. So there's a spectral decomposition that we've been talking about right here. Now I want to see the projectors that make up that spectral decomposition. So in group theory, you kind of play the thing backwards. You get the projection operators themselves sort of at last, there's a last step. So these things are all going to give us modes. That's the deal. And let me go ahead on here just so we catch up for this thing. Oh dear, I'm going the wrong way. Here we go. Okay, so that's what I want to show is the actual waves that you make by doing this. And also the quantum numbers that go with it. That is something that I think is neat to see. Now we'll animate these things, but that is well, I should probably do that right away. These are the coefficients of the spectral decomposition, starting with just all ones, and then a 1, and e to the minus 2 pi over 3, to the plus 2 pi over 3, and then this switched. Those are orthogonal eigen states. One of them is a wave that's moving that way, and the other one is a wave coming back. And we'll see more complicated examples of these which have the structure that I really want to show. But this is already good enough to give you a pretty good feeling for that. So what I think I'll do is, and again, I'll play these things. The actual Hamiltonian solution is very easy once you've done this, because you now know the eigenvalues of all of the group operators that are in the Hamiltonian, and these are just coefficients that you would vary depending on the strength of each one of those connections. As, say it was a quantum mechanical problem with waves, it would be tunneling coefficients. So I'll put this here for now. But that gives you the H eigenvalues very quickly. And it gives you the K eigenvalues as well. The basic idea is that the H eigenvalues is that matrix which is B, and this one has the B squared or K squared. These, this Hamiltonian, I should say, this K matrix is the square of this one. And so the eigenvalues correspondingly are that. So these are the display of the thing. If you were working with a quantum mechanical system that has triple symmetry, or if you're working with a classical spring mass system, then what you get is the square root of the numbers that you get here if you're looking for the frequency for the spring system. So that makes this, you know, really an easy problem to solve that has the symmetry of sort of giving you the answers for free. Now all of this has to do with the scaling that's associated. There's a lattice constant, and that's n times a lattice spacing. These are standard things that you find in a solid state physics book, and this is the Ks and lambdas that go with the waves that we've just drawn here. Now, see if there's anything else I should point out. Let me take this one ahead as well. There's something down at the bottom. It's not showing too well here, but the notation for this that we use is just an integer modulo the symmetry number. So when we say that, see if I've got that written at the bottom here. Yeah, this one I can read pretty easily. When you say that you're naming something that's 4 mod 3, and then actually what we're doing here is 0 mod 3, 1 mod 3, and 2 mod 3, we're done. But 2 mod 3 is the same as minus 1 mod 3, and 1 mod 3 is the same as minus 2 mod 3. So this thing is going around and it's counting over again. So higher levels of this is a solid state problem that was electronic and went to the next band, you would be going next with 4 mod 3. The remainder of 4 divided by 3 is the correct name for that expression. We write it as a subscript here when we say 2 mod 3. Okay, secretarial details that are important for this. Okay, so these the modes that these things make can be either standing waves or moving waves. The moving waves are complex. I colored them green because they're going somewhere. I should really be coloring these ones red because they just stand. They're linear combinations, that is, sum and difference of these give these. And they don't go anywhere. They're standing waves. And you can see that this thing just goes up and down twice as far as this one. So it's probably useful at this point for me to go ahead and get the animations going that go with these two modes. That's a picture of them actually in motion right there, but static. Could be longitudinal too. That's not a problem. Let me drop back here. This one seems to work better, so I'll use the animation that came with this, I think it was called the N3 wave. Let's see if that's what I'm after. Yeah, now this is the moving wave right here. And what you're seeing is the sort of phasing that would occur on all those power lines you see out in the plains that have 3 wires going along. The 3 wires, it's called 3-phase. There are the 3 phases that they would have if you could slow their motion down and actually see the phasors at work in them. Now this is, I believe, if I want to fool around with this thing, I'm going to try to do that. First of all, I'll kill everything here. This is the 0 mod 3 wave right there. And if I let that phaser turn,
Resume. Resume button at the top.
oh, I can do that. Resume here.
I'll keep it there.
Yeah. And
When it's stationary.
this one, I guess has 0 eigenvalue, so it's not going anywhere. But let's kill it and make one like this. Okay, so this is a moving wave, which, if allowed to go, would go that way. Okay, I'm going to kill it. Go back to Fourier control here. I think I can do it directly here. Do this one. Okay, it kind of looks the same, but the phases are different. And this is an important lesson right here. Oops. Let me go up here like this and resume this one. This one goes this way. Now, how do you tell by looking at a static wave which way it's going to go if you don't have animation? And you just use that rule that whoever is ahead in phase gives. So this particular phase right here at 3 o'clock is quite a bit ahead of this guy, so we're 10 o'clock. So this guy is giving to this one. But this one is also connected to this one. And this one is ahead of this guy right here, okay? So he has to be giving to this one. And if it's all equal amplitudes and equal phase differences, you have an even wave that does not grow or shrink, a perfect moving wave. It's all in the phase. Keep the phase, baby. Okay? And if you do keep the phase, you have a wave that is a perfect moving train. Okay? And that's simple mechanics, but it's also true as this is giving action to this one, if you're talking about quantum mechanics. Worth knowing. Okay. Now, if I take, and I don't know if I can do this really quick here, I'm going to go ahead here and put an equal amount of this one, almost equal amount, and that's probably pretty close right there. And when I resume on that one, well, it doesn't look like anything's going anywhere. This is a standing wave, right? Good old-fashioned cosine standing wave. So this one right here is taking as much from this one as this one is giving, so it doesn't grow. Okay. Well, anyway, this sort of animation, a wave, it lets you do really complicated waves that I'll try to show a little bit of that before we quit here. The things like this is C6 here, that has a good deal more structure. I'm going to go ahead and see if I can get it to run a little bit here.
And I recall those are static images, so that doesn't quite give you the full stacked waveforms. But
really
those links
like
on that page will take you there.
What is it that's wrong with this computer that it will not. Let's just go ahead and put this thing. Let me just see if I can
Appears
make
to
it.
be a network issue, so bounce the network.
Just turn the Wi-Fi
Right.
off. That's
Yeah,
what
you
happened.
bounce that and it'll
Let's see
give
if
us
I
a
can.
chance.
There we go. Okay. Well, that's the character table, but if I want to actually see the FOIA controls for that thing, this is the deal right here. So there's a typical wave that isn't going to go anywhere if I resume it, because it has zero eigenvalue. But the rest of the spectrum is more complicated. If I also put this guy up, I make a what would turn out to be a standing wave. Let's see if that in fact works.
Why don't you follow those links on that one page?
Pardon? Oh, yeah, that probably
That's
would
why
be.
they were prepared. This originated from a static application. All it
Oh.
does is render. It
Okay.
isn't meant to run. It's just those
Yeah.
phasers in tabular form.
Well, we can go get a scenario, I think, that might be worthwhile. Let's take 12. So there's the typical phonon spectra right there. And then we have a Fourier control right here that lets us do that. Let me zero that. I'll set up first a moving wave going in the one direction and then one in the opposite direction. That's a pretty good standing wave right there. Let's resume that. Yeah, so there's the typical standing wave. Now what's interesting about this is if you kill all this stuff, let's pause it and kill it, and start with a one of these. Let's just pick that one for the heck of it. You see what happens is I produce a delta function, or very close to one. Now if this were a nice linear dispersion, and I started it up, it would behave in a very nice way. This is not going to behave in a nice way. I can go ahead here and resume it. It just gets lost, seems to get lost, and that's something there's some pages ahead where we discuss that in some detail. But if I pick the, see if I can find a way to do that. I guess I'm not able to set that particular case up here. I have to adjust those spring constants to make a linear.
The dispersion, second from the bottom, change to 0 to a 1.
Okay, this is this one right here.
It's
Let me see if I
hidden
can.
away there. Sorry
Yeah,
about
make
that,
it a
folks.
first order dispersion. Okay, let's see how that runs.
Just go ahead and launch it.
Launch. Okay, there you go. And this is the dream of all of the quantum chemists that hope to, give energy to something and have it hang together. That is, have the pulse hang together. If you can make a linear dispersion like that for frequency versus k vector, you get to play that game. It doesn't just disperse and become chaotic. So that's a really important piece of wave forming waves in quantum systems, but also the various laser waves. I'm thinking of coherent states in optical and quantum optics. Finding ways to do that is very important piece of work, being able to keep energies. Like when I talked about the trebuchet, it would be able to keep its energy and make the final arm go supersonic. That's kind of what you would have to do to make that happen. Okay, well, we're sort of out of time here, so I'm going to go ahead and quit. But I recommend you take a look at some of the stuff that follows after this, and maybe we'll use next class to talk about that, which involves these very, very strange sort of dispersion functions. If you take the Fourier analysis of the dispersion function seriously, that's what symmetry analysis is really about. So we'll talk about that on Wednesday, 2 days from now. Okay.